What's up, mathematicians? Justin here, and welcome back to our unit on measurement. This is lesson number 6, called Applications of Trigonometry. In this lesson, we'll use those tools for measuring right triangles that we learned about in the previous lesson, and we will use them to solve some application problems related to real-world situations. Let's go ahead and dive right into our first application. So in this first example, we will revisit the scenario from lesson 2 where we use shadows to find the height of a tree. And here's the diagram that we used in this situation. Now, we discovered that the height of the tree was 16.7 meters, but there are some other questions we could inquire of this situation. One of them is, what was the angle of the sun? And another one might be, what was the time of day? Let's use our trigonometry tools to answer those questions. So first of all, we're going to need a triangle here, and let's go ahead and put in the measurements. We'll go ahead and use the smaller of the two triangles. They're similar triangles. You can use either one because they're proportional, but we'll use the one based on the person. So the height is 1.6, the rise, if you will, and the run is 2.4. So let's write those in. We have 1.6 meters and 2.4 meters. Now we don't know the length of the hypotenuse. And in the previous lesson, I mentioned that you could just divide everything by the hypotenuse. But in the case where you don't know the hypotenuse, it doesn't actually matter. Let's go ahead and just write the values of opposite and adjacent. So the opposite is equal to let's actually specify the angle too. So this is the angle we're interested in, right? The angle of elevation of the sun. And I will put a theta there to indicate this is my unknown angle that I want to solve for. Okay, so I have my opposite, my adjacent, and hypotenuse. Now, from the perspective of this angle, this is the opposite. It's the rise. And from the perspective of this angle, this is the adjacent, the run. So 2.4, and as I said, the hypotenuse, I don't know. Well, this means I'll be using the tangent ratio. So let's go ahead and set that up. We'll go ahead and say that the tangent of the angle is equal to the opposite, 1.6, divided by the adjacent, 2.4. Well, if I take 1.6, divide by 2.4, plug that in a calculator, I'm going to get 0.067 rounded to the nearest hundredth. It's actually 0.6 repeating, but this is what I get when I round it to the nearest hundredth. So if the tangent of theta is equal to 0.67, then what is the actual value of theta? What is the angle? Well, we can look this up in a table as we've done in the past. So let's see, here's my table, and I'll go to the tangent column, and I'll just go down until I see something that's around 0.67. And we see right here, okay, 34 degrees is the closest. If it's actually a bit more than 0.67, but if I go down to 33 degrees, I'm farther away. So if I'm going to go to the nearest degree, it's going to be 34 degrees. So theta is equal to 34 degrees if I'm rounding to the nearest degree. Now, if you want to be more precise than that, of course, you can plug this into a calculator. And let's look at how we could do that. So because we are actually looking for the angle and we know the ratio, we aren't going to use the tangent, we're going to use the inverse tangent. So I hit second tangent, and you see there has tangent to -1. That means inverse tangent, which is also, by the way, called the arctangent. And my ratio is I can just include even more significant digits because it's on my calculator. And I get this, 33.7 degrees. So if you want to round to, say, the nearest tenth of a degree, it would be that. It would be 33.7 degrees, which, if you round to the nearest degree, of course, is 34 degrees. Okay, so what does that mean? That means that the angle of the sun when these measurements were taking place, if these were real measurements, which I actually just made this up when I made up the problem, but if these were real measurements, then the angle of the sun when the measurements were taken would be 34 degrees. Okay, so a follow-up question might be, what time of day did these measurements take place? Okay, so you can see here that I have the website suncalc.org pulled up, and I can use this website. You can plug in a location, a date, and you can use it to determine the angle of elevation of the sun, among other things. So I wrote this problem a few weeks ago, so I just went ahead and put January 1st for the date. This was a few weeks ago. I live in the Pasadena area, so you see it's centered at Pasadena. And so now I can move this around to different times, and then it shows the location of the sun changing. Okay, kind of a cool website to play around with. I will include a link in the description if you'd like to play around with it. I would encourage you to do so. But the thing here that I want to do is I want to find out when this altitude, which you see right now is 24.04, at what time will that altitude be 34 degrees? So, of course, earlier in the morning, the sun is at a lower angle. And you see it gets higher and higher and higher and higher. And as we reach the highest altitude, that's interesting. What happened there? So it turns out that on January 1st, the highest angle of the sun was around 33 degrees, which means that if I took these measurements accurately and got 34 degrees, I must not have done it on the 1st of January, right? Because at no point during that day did the sun reach an angle of 34 degrees, which, by the way, if you're a teacher and you want to see if your students are fudging their data, you could try this out. Make sure that their angle and time of day, you could ask them, what time of day did you take the measurement? Make sure that it makes sense. And I guess if you're a student, now you know how to avoid being discovered for fudging your data. But anyway, in order to get the angle that we're looking for, we'd have to choose a different day. So today is actually the 17th of January. Let's see if the 17th of January will give us an answer. And we see now it goes up to 35 degrees. So this is going to work. And let's get as close to 34 degrees as we can. So right around here, we're almost exactly at 34 degrees. And we see that the time is 11:12 in the morning. So at 11:12 in the morning, these measurements could have been taken. And of course, as the sun goes down, there's another time in the afternoon that we could have taken these measurements. So let's get it again as close to 34 degrees as possible. That's quite close. And this would be 12:53 p.m. So those are the two times of day when this particular scenario could have existed in Pasadena with that angle of the sun today. All right, so let's go on to our second example. For this example, let's imagine that there's a bird watcher looking up at a bird's nest, and they want to know how far away they are from the nest itself. Okay, so here's my situation. This is my tree with a nest up top. It looks like it's probably one of those big eagle's nests or osprey's nests or something like that. We'll go ahead and assume that this tree is straight and vertical, perpendicular to the ground, which makes this a right angle and giving us a right triangle. We'll also say that our bird watcher is relatively tall, and the distance from the ground to their eye level is 2 meters. Okay, so pretty tall bird watcher. And now, in order to find out this distance from where they are to the nest, this distance right here, the thing we're trying to find, we'll need two pieces of information, right? You need two pieces of information in order to do trigonometry on this triangle. So the two pieces of information that this bird watcher could probably collect if they had the tools, had some measurement tools, would be to find this distance between them and the tree. So let's mark that one in first. And we'll go ahead and say that they've measured this distance to be 22 meters. And then they would also need to measure this angle of elevation from their eye level to the nest. Now there are phone apps that you can use to do that. It's actually not that difficult. Let's go ahead and say they've done that, and they've come up with a measurement of 18 degrees, an angle of elevation of 18 degrees. So in these, given these measurements, what is this length right here? Okay, so as I shared with you in previous lesson, one approach to this is just to sort of simplify this down and turn it into a unit right triangle. And the way to do that is to divide every side by the value of the hypotenuse, right? A unit right triangle is a triangle in which the hypotenuse has a length of 1 unit. Well, if you divide everything by the hypotenuse, the length of the hypotenuse, then you're going to get a 1 here. So right here, this becomes x over x, which equals 1. This becomes 22 over x. And then I have this side right here, which we're actually talking about this particular, not the entire height. And this, I don't know what it is, and I don't really care, because the problem is asking me to find this length, not to find the height of the tree. Now, you could find the height of the tree by including this 2-meter height if you wanted to, and maybe we'll do that at the end, but we'll start by finding this length right here. Okay, so you'll notice that I am looking right here at the run, the cosine. And the run, when I scale this down to a unit right triangle, is 22 over x. So I can write that the cosine of, oops, sorry about that. The cosine of 18 degrees, I almost wrote theta, but I actually do know the angle here. Cosine of 18 degrees is equal to 22 over x. Now, in order to find out what x is, I would need to multiply both sides by x. Okay, well, these cancel out, and I get that x times the cosine of 18 degrees is equal to 22. Now, in order to solve for x, I would divide both sides by the cosine of 18 degrees. So let's go ahead and do that. Divide by cosine of 18 degrees. Divide by the cosine of 18 degrees. Now, by the way, you could always find out what the cosine of 18 is first and divide by that number, by that ratio. You'll get the same answer. But if we follow through with this approach that I have here, I'm going to see that, okay, x is equal to, let's go ahead and plug in a calculator, and let's see, I've got 22 divided by cosine of 18 degrees. And I get 2.1 if I round to the nearest tenth. Okay, so wait a second. That doesn't seem right. Cosine of 18 degrees? Okay, I just realized the mistake I made. I wanted to type in 22 divided by the cosine, but I typed in 2 divided by the cosine. I saw this, and I was like, wait a second. That does not seem far enough to be the distance. So let's try that again. 22 divided by the cosine of 18. That looks a lot better, 23.1 meters. So when you're doing these calculations, it's always a good idea to sort of ask yourself whether the numbers you're getting make sense. And that makes more sense to me based on the way I've set up this problem. So x is 23.1 meters. Let's go ahead and put a box around that. Okay, so what is the distance from the birdwatcher to the nest? It's 23.1 meters. Now, let's imagine you also wanted to find the height of the tree. So in this case, the height of the tree we'll call this h. Actually, h is not the height of the tree. H is the distance from here to the top of the tree. And then we'll have to add in this extra 2 meters. So oftentimes, you know, on different tests and such, they'll include a problem where you have to add an extra little bit. So you always have to keep that in mind if there is a height of the person or something, to add that in later. Okay, so how do I find this height? Well, this one I'll solve in, I guess, the more conventional way, rather than dividing everything by the hypotenuse as I did here. So the more conventional way, my approach to it is to do what I did in the last problem and just write opposite, adjacent, and hypotenuse, and find out what the values are from the problem. So in this particular situation, the opposite is the thing I want to find out. So that's going to be h. The adjacent is this length right here, 22. And the hypotenuse, I actually do know it now. It's 23.1. So since I know both the adjacent and the hypotenuse, I could pick whichever ratio. Well, I can't actually pick any of them because it has to include opposite. So I could not pick cosine, but I could use either the sine or the tangent. But if I didn't know the hypotenuse and I knew the opposite and the adjacent only, I would have to go with the tangent. So let's go ahead and use that approach. So I would say here, okay, the tangent of the angle 18 degrees is equal to the opposite h over the adjacent 22. Now, in order to solve for h, I multiply both sides by 22. Those cancel out, and I get that h is equal to 22 times the tangent of 18 degrees. Let's go ahead and plug that in the calculator. And so here we go, 22, not 2, times the tangent of 18. I hit enter and I get 7.148. So round to the nearest tenth. I'm going to get that h is equal to 7.1. Now again, that's not the height of the tree. Okay, in order to get the height of the tree, I need to add that extra 2 meters in. So I'll write it this way. I'll just write tree height is equal to 9.1 meters. So that's 7.1 plus the 2 meters height from the ground to the eye level of the birdwatcher. All right, so now we've solved for both the distance from the birdwatcher to the nest and also, as a bonus, the height of the tree. Okay, so I'm going to do just one more example before wrapping up this video. And for this example, I'll show you how you can use trigonometry to find the height of something like an antenna that's on top of a building. So here we have my building, and here is the antenna. And we're going to go ahead and say the angle is measured from a point on the ground to simplify things just a little bit. We don't have to add that extra little height in. So what do we need? We're going to need, first of all, some angles here. And so let's go ahead and say the whole angle of elevation up to the top of the antenna. Let's go ahead and say that that is, let's say 34 degrees. And then I'll use a different color to make sure that we're being clear here. So this smaller angle of elevation, which is just the angle of elevation to the top of the building, let's go ahead and say that's, I don't know, about 28 degrees. So now we'll need the distance from the point that the angles are being measured to the building. Let's say that that distance is 55 meters. And using these pieces of information plus the assumptions that we've been making, right, that the angle sums are all the same and that this building is in fact at a right angle, it's perpendicular to the ground, all those types of things, we can now find the height of this antenna. Now I'm going to label a couple things here. So first of all, I want to label the overall height, and let me actually draw that in. Right, so we have the overall height of the building plus the antenna. Okay, so let's go ahead and label that H, and then let's label just the height of the antenna X. We'll want to use two different variables here because, you know, this height obviously is not the same as that height. So we're going to need to find the overall height, and then we'll also need to find this height in order to find that height. So actually we'll need another variable in there too. We can go ahead and call that one y. All right, so let's start by finding the height of just the building, which is y. And in this smaller triangle, let's indicate what I know. So I know that the opposite, the rise, is equal to y. The adjacent right here is 55. And then the hypotenuse is this length here. I don't know what it is, but I also don't care. So I'll leave it blank. And now in order to find the length of y, I can use the tangent ratio, right? Tangent is opposite over adjacent. So I'll go ahead and say the tangent of this angle here, 28 degrees, is equal to the opposite, which is y, divided by the adjacent, which is 55. Okay, now in order to get y by itself, in order to solve for y, I'll multiply both sides by 55. Those cancel out, and I'll go ahead and plug this in my calculator here. Let's see, 55 times the tangent of 28 is 29, and my unit here being meters. Okay, so that means that y is equal to, and I'll round to the nearest tenth place, 29.2. Oops, sorry, couldn't see what I was writing there. All right, now let's solve for the total height. And I'll use that. I'll do that one in orange because I indicated this angle in orange. Maybe I should have written this h in orange as well. Okay, so for the total height, my opposite is equal to h. My adjacent is the same. It's still 55. And my hypotenuse, once again, don't know and don't care. So I don't have to worry about that one. Once again, I will be using the tangent ratio here. So here the equation is that the tangent, but now I use this angle here, this 34 degree angle. So the tangent of 34 degrees is equal to the opposite, h, divided by the adjacent, 55. Now to solve for h, I will multiply both sides by 55. These cancel out, and I get 55 times the tangent of 34 equals h. Let's plug that in the calculator. And 55 times the tangent of 34 degrees. And you see here I get 37.1 meters if I round to the nearest tenth. So I get that h is equal to 37.1. Okay. Now using these two pieces of information and the diagram, I can discover what the value of x is. So let's use a different color here. Indicate that we're talking about a different magnitude. So I'll put this one also in the magenta color, I guess this is. So I know that x is equal to this height h minus the building height, which is y. Okay, so let's see, h is 37.1, and y is 29.2. Okay, so if I take 37.1 minus 29.2, well, let's see. If it were 37.1 minus 29.1, it would be 8, but I'm taking away 1/10 more, so that would be 7.9 meters. So I'll go ahead and write it down here. X is equal to 7.9 meters, and that would be the height of the antenna on top of the building. All right, that'll wrap up this video. In the next video, I'll show you how I've used some right triangle trigonometry in some woodworking applications in my own personal life. As always, thank you so much for watching. If you learned something, please like and subscribe, and I'll see you in the next video. Bye-bye.